Just give me a minute. I am starting the live streaming.
Hello. Hello. Is the class on right now? Because I cannot hear anything.
Yes, class is on.
Ma'am isn't currently teaching anything because she's setting up the live streaming on her end. Maybe wait a
Okay.
little
Okay.
bit.
Okay. 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 Yeah. Because I couldn't hear ma'am teaching. That's why I asked.
Okay, so the live streaming has started and the link is there in the chat if you want. Okay.
Okay,
Fine.
ma'am.
Okay. So in week one, mainly we are going to see what are vectors and what are matrices. Okay. And then we will see what are system of, yeah. Any question there? Okay. What are system of linear equations and how to solve them. So how to solve them, that part today we will not be covering. I guess someone is asking something. What is that?
Ma'am, your screen is not visible.
The screen is not visible. Okay, just give me a minute.
Others who are not speaking, please mute.
All right.
Yes, ma'am. Now visible.
Okay.
Yes, ma'am. It is now visible.
And,
So
and before starting, can you introduce yourself?
okay, fine. Yeah, as I told you, my name is Lavanya, and I did my PhD from IIT Madras. So for this course, I will be the instructor, and one more instructor is also there. All right. Okay.
Ma'am,
Okay.
will TA sessions will also conduct all?
The TA sessions.
Will also be conducted all? Cause in calendar only open sessions are there.
As I told you in the beginning of the session, the TA sessions will be on Tuesday and Saturday.
Okay.
Does not have a schedule. I will check it and make sure it is updated. Okay. All right. Okay. So, video here. Yeah. So, what are vectors and why do we need vectors? So, you people are studying this data science course. So, this is mathematics for data science. So, in data science, you see that there are many
Ma'am, your
data
voice is
to be
lagging.
dealt with. Okay.
Yes.
And to handle data, vectors play a very basic role.
Your voice is lagging.
Ma'am, your voice is
After
lagging.
data science, it
Yes.
started
This
to
is not
lag.
clear. We can't hear.
I believe ma'am can't hear us either.
Is it so for everyone?
Yes, ma'am.
Yes, ma'am. It's for everyone.
Yes, ma'am.
Yes, ma'am.
Am I audible?
Yes,
Yes, you are
Yeah, ma'am.
audible.
Right
Ma'am.
now you're audible.
Yes, ma'am.
Yes,
Yes,
Am
ma'am.
I audible?
You are audible.
Yeah.
Yes.
Ma'am, you are audible. Voice breaking.
You're audible.
Okay, fine. Okay. So for representing data and for also doing some calculation in the given data, vectors play a very important role. So what do we already know about vectors? You know that vectors are something which has both magnitude and direction. And in physical context, you know that you represent vectors with arrows like this, right? And the length of these arrows represents the magnitude of these vectors, and this pointed arrows represent the direction, right? So this is what you already know about vectors. But what we are going to look for this course, we'll see now. Okay. So a vector usually can be thought of as a list. Okay. So a list, or sometimes you call it as a tuple. Okay. So for example, you see this data. Okay. This data represents the different dimensions and also the weight of a set of 8 carton boxes. Okay. So here you see the length, height, width, and weight. Okay. So now each of these length attributes, length, height, width, weight, do they represent a column or a row?
Column.
Please zoom a little bit.
Column, ma'am.
Yeah. So you see that there are 4 attributes here, and each of these 4 attribute, length, height, width, and weight,
It's column.
each of them are representing different columns.
Column. Yes, ma'am.
Right?
Columns.
Okay. And each of these cases, the details of carton 1, carton 2, each of this, all this,
Rows.
they are
Rows.
representing rows.
Rows.
Okay. So each of this is a row. Okay. So if you are considering the details of just one carton box, for example, if I am considering it as a tuple. Tuple means you have the value separated by commas. Okay. So now this is a row vector. Okay. Suppose I am collecting all the length together.
Ma'am, what is the difference between tuple and vector?
See, tuple is just a name, but vector has a wide meaning, because vectors in vector spaces, all the elements are called vectors. Okay. Tuple is just a name for this kind of representation.
Your voice
Okay.
is not. Your voice is lagging. Actually.
Ma'am,
Now also the voice is lagging.
No,
Yes,
it's
fine.
fine, ma'am.
Yes, ma'am.
Okay.
excuse me, ma'am.
So yeah,
What is the difference between vector and tuple?
that is what I was saying. So you see that
Sorry, the
tuple is just a name for this kind of a representation.
list
Okay.
and tuple. What is the difference between list and tuple?
See, list, you can call this as a list, you can call this as a list, but usually tuple is something which has this kind of a representation.
Separated by comma only.
Okay, like are separated by commas.
Okay, thank you.
Okay, fine. And this is a row vector, and this is called a column vector. Okay. Suppose, let's say, those who are manufacturing the carton boxes or those who are ordering the carton boxes, they are demanding for carton boxes whose length is double the length of this, or whose width is double the width of this. Then what do? You just take this particular column vector and multiply it with 2. Rather than multiplying each of these separate values by 2, so it is easier when you just have to multiply the entire vector by 2. Okay. So in that way, these vectors are helping us to reduce the number of times you are writing certain commands, or certain calculations are simplified in this way when you are representing the data as vectors. Okay. So the main thing you should know about vectors from a given data is that, so from a given data, either you can have column vectors or you can have row vectors. Okay. So column vectors are represented in this way, and row vectors are represented in this way. Okay. So
Okay,
we'll
ma'am.
see one more. Yeah. Yes. What is the question? Okay. The number of passengers, the next example is here. The number of passengers traveling in different time interval for 16 trains traveling from a specific starting point is given below. So there are 16 trains starting from a specific point. Okay. And within each 15 minutes time interval, how many passengers are traveling in the train? That data is given here. Okay. So for example, if we want to know the details of the train 6, do you get a row vector or a column vector? How do
Row
you
vector.
represent the data?
Row vector. Row vector.
Yeah,
Row vector.
it is a row vector, right? So you have 14, 97, 18, 0, 0. Okay. And suppose you want to find what is the number of passengers in each train in the first 15 minutes, then you know it is a column vector having how many components? 16 components, right? So 173, 148, and then it goes on, and you have 16 components. So you see that then we don't have any restrictions for how many number of components should be there in a given vector. Okay, it can be any finite number of components for a given vector. Okay, fine. So in this case, you see for the row vector, there are, I missed some number here. There should be, no, it's fine. So for train 6, the row vector has 5 components, and then this column vector has 16 components. Okay, fine. So in the context of the above examples, vectors could be either columns or rows. Okay, so vectors can be used to perform arithmetic operations on lists such as table columns or rows. Okay. So here is an example, a simpler example to show how to perform arithmetic operations. So the marks obtained by Kartika, Romi, and Farzana in quiz 1, quiz 2, and NSEM. Okay, and with maximum marks of each being 100 are shown in this table. Okay, So now choose the following set of correct options. Just go through the correct options given here and see which one is correct. I'll just give you a few seconds. Please go through. So the first option here is marks obtained by Romy in quiz 1, quiz 2 and NSEM represent a row vector. Is this correct?
Yes,
Yes, ma'am.
Yes, ma'am.
Yes.
Okay.
Yes, ma'am.
Quiz 2 marks of Kartika. So quiz 2 marks of Kartika. What is the quiz 2 mark of Kartika, Romy and Farzana?
Ma'am, it's correct. It's a
Column
column.
vector.
Column.
Column.
Yeah, it is a column vector. So
column vector.
So 50, 41 and 21. So this one here, the row vector here is for Kartika, it is for Romy, right? So 33, 41 and 45. This is the row vector given here. And what is the column vector here?
50,
50,
41,
41 and 21.
41.
So this is the column vector. Okay, fine. The number of components in column vector representing quiz 2 marks are 9. So
False.
quiz 2 marks, how many components
Wrong.
are there in the column vector?
3.
3.
3.
3
One,
only.
3 are there, right? So this 9 is incorrect option. Okay, fine. What about option 4?
It's correct.
This one is correct.
Option 4 is
Yeah, number of components in row vector representing row mix marks are 3. So this is correct. Okay, so is this clear for everyone?
Yes, ma'am.
A very simple
Yes,
exercise. Okay. Now, in order to improve her marks, Farzana undertook project work and succeeded in increasing her marks. Okay, her marks became doubled for each exam. Choose the correct option. Okay, so now Farzana has did some project and her marks doubled for each exam. Okay, so what are the marks of Farzana first of all?
38, 21 and 35.
21 and 35.
Okay, now if her marks are double, then what is the vector you are going to get?
76, 42 and 70.
So 42 and 70.
70.
All right. Okay. So to obtain the marks obtained by Farzana after completion of the project, scalar multiplication has to be done by 2 to the row vector representing Farzana's marks. Is that correct?
Correct.
Yes, ma'am. Correct.
Yeah.
Correct.
Yes. To obtain the marks obtained by Farzana after completion of the scalar multiplication has to be done by 1 to the row vector, which is of course incorrect, right?
Yes, ma'am. Incorrect.
Yes, incorrect.
Yeah. After completion of the project, the row vector representing Farzana's marks is 76, 42 and 70.
Correct.
Yes.
Yeah, correct, ma'am.
Correct.
And you see that, of course, this is not the correct answer. So option 4 is incorrect. After completion of the project, again, some other values are given. So it is also incorrect. Okay, is it fine? Okay.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yes.
Yes. Following Farzana's improved marks due to her project, okay, that is her marks become doubled for each exam. All the students were given bonus marks in quiz 2. So it means what? Now we are going to consider instead of 38, here 76, here 42, and here 70. Okay. Now what is happening? All students were given bonus marks in quiz 2, which is given by the column vector 10, 12, and 15. So is there any mistake here? Because, okay, these are the bonus marks. Fine. So what are the bonus marks?
10, 12.
Bonus marks in quiz 2. So 10, 12, 15.
12, 15.
Okay. So what will be the column vector representing the final marks obtained in quiz 2 by Kartika, Romy and Farzana?
60, 53 and
83.
57.
50.
Yeah.
742.
Okay. So you have 60, 53 and 57.
57.
Okay, so these are the updated marks. Okay, so you see how representing it as vectors are useful for making some calculations. Okay, fine.
Yes.
Okay, so in general, all these vectors, whatever we are representing, we call it as Rn, which is the Euclidean space. What is Rn? The set of all n tuples. It means you are having n components. So 1, 2, 3, n components you are having, where each of these components are real numbers. all this collection in general we represent it as Rn. Okay, so in that case, can you say where does this element belong to? 60, 53, 57?
R3.
It is an element of R3. Okay, so this symbol writing like this is kind of a mathematical notation. Okay, so just to represent that it is representing a real numbers, not just any R. Okay, fine.
What is R1, R2, R3 again?
Yeah, I'll tell. So what about this one?
R5.
R5.
R5. And what about this?
R16.
R16.
Okay. So in that case, what about R? It is
Single
simply
line. One.
set of all real numbers. Okay. R is simply the set of all real numbers. And what is R2? R2, you know, it is simply the set of all x1, x2, where x1 and x2 are in R. They are real numbers. Okay. R3, same way, you will have three components. Okay. So R2 means you know that it is the usual plane, xy plane, which you see. Okay. So R2 means the usual xy plane which you see. Okay. And each of these coordinates x1, x2, how do you represent them? For example, let us say you have some point, maybe 1, minus 5, 2, 4. How do you plot them in this graph?
One on
one
x-axis
X
and minus
is
5
1.
in y-axis.
Yeah.
Minus 5 y-axis.
So minus 5 is not there here. So in this graph, so maybe I'll put
Minus
3. Okay. So 1, minus 3 is this vector here. So you draw this line with an arrow here. So this is the vector 1, minus 3. Okay. And what about the vector 2, 4?
It is in first quadrant.
First quadrant or
Right. So this is the vector 2, 4. Okay. So in general, you see that any point A, B. Okay. So this represents a distance along x-axis from origin. And this point B, this is the distance along y-axis from origin. Okay, so these are the points in R2. Okay, fine.
Yes.
So now how to add two vectors? Suppose you are having, yeah?
I didn't understand what R2 is again.
About R?
Yeah, R2 and R3. What is R2 and R3?
See, R2 and R3 means all the two tuples. So it means you have two components. So you have first component which represents the distance along the x-axis.
I think R2 is there are two. If there are two components, this is R2.
Sorry?
If there are two components in a row vector or column vector, then it is R2. I think.
See,
is it correct?
either you can represent it as a tuple like this. As a row vector, you can represent, or you can represent it as a column vector. Both are representing the same point in R2. It does not matter whether you represent it in this way or this way. Both are equivalent.
Ma'am?
Yeah?
R3 is a 3-dimensional.
Yeah. I'm going to cover it next.
Okay.
Okay. So, how to add two vectors in R2? In R2, you can actually, in general, the addition is same for almost all the vectors for Euclidean spaces. But in R2, it is easy to visualize using diagram block. Okay.
Hello.
So you can visualize the yeah.
Yeah. What is the meaning of R2? Two dimension.
Ma'am, does the two represent the number of components in either row or column vector?
Yes, exactly. This 2 represents the number of components. So, for example, here Rn means you will have n components. Okay, and R2 means.
Okay, thank you, ma'am.
Okay.
Yeah, got it, ma'am.
Fine.
Ma'am, just asking, is this there in the lecture? Because I didn't see it in any lecture. I'm just.
It is there in the lecture.
Okay.
Okay. Fine. And how do you add two vectors? So suppose you are having, let us say, two vectors x1, y1 and x2, y2. These are vectors from R2. So how do you add them? You are adding them coordinate wise or component wise, you are adding them. So the first components you are adding together,
X1 plus
and the
X2.
second components you are adding together.
Y1 plus Y2.
Okay. So component wise addition. This is what you call as component wise addition. Okay, first components are added together and second components are added together. In general, for any vector from Rn also the same rule goes. First of all, let us look at the vector addition in R2 and how does parallelogram come into picture here. Okay, so maybe let us take some other vectors here which has easy visualization. So let us maybe take this vector. Can you tell what is this vector here?
Y cap.
2, 0.
2,
0, right? And let us take some other vector, maybe this one here. Can you say what is this vector?
1,
1, 1.
It is 1, right? Okay. So now let us complete this parallelogram. Okay. And what is this point here?
3, 1.
3, 1. And you see parallelogram law says that, so if you have two vectors, then the diagonal of the parallelogram here gives you the sum of these two vectors. So in fact, if you see what is the component wise addition, you will get the same 3, 1. Okay, so this is called the parallelogram law. So you don't have to worry about the parallelogram law, the proof of the parallelogram law and all. So just to know that this is what is happening in R2. Okay. And the addition is very simple. You don't have to always draw the parallelogram and see what is the sum. You know that you can just simply add this component wise. So this is just to see geometrically what is happening when you do addition of two vectors. Okay, particularly in R2. Okay, so mainly all the visualizations we are seeing in R2 and R3 because that is where we can visualize things. Okay, but in Rn also the same things will apply, but we will not be able to visualize after 3 dimension. Okay. Yeah, is there anything, any question?
Ma'am, one thing I have learned that for vectors, they must follow parallelogram law. Then only they are vectors. Not only magnitude and direction is required. This is also a requirement. Is it true?
See, magnitude and direction, this concept, yeah, in the physical sense, this is what is there. But with respect for this course, what are vectors? I will tell you at the end. I will say what in this course, what do we mean by vectors? Okay. After a few slides, I will tell. Okay.
Hello.
Yeah.
Just a minute, and can you just a little bit about the slide? I want to see the top slide. Yeah. No, little lower, a little bottom. This says point A, comma B. That 3 lines, what does it represent? Vector AB is equal to AI. How do you read it out? AI, there is a mark on the top, no? The symbol on top.
Okay. So this, see, usually this I and J represents the X and Y directions. Okay, the unit vector along X and this is the unit vector along J.
Okay.
Okay, so I don't know what color, maybe some color like this. So this is your I and this is your J.
Okay.
Okay.
Okay. And the 3 line represents direction?
I told you this 3 line is kind of equivalent
kind of thing.
Yeah.
Okay.
Fine. Okay.
Yeah, thanks.
Yeah.
Ma'am.
Okay. So.
Hello, ma'am.
Yeah.
Ma'am, can we subtract?
Yeah. We'll come to it next. Yeah, we'll come to it next. Step by step. Okay.
Hello,
Next, let us see what is meant by scalar multiplication. What are scalars? So scalars may have different meaning. It can be complex number, real numbers, but in this course, by a scalar, we always mean a real number. Okay, by a scalar for this course, we always mean by a real number. So multiplication by a real number. Okay, so let us take any vector, maybe a simple vector 1, 1 I'm taking. Those who are not asking any doubts, please mute yourself. Please. This is an instruction for all the classes. Throughout the classes, please make sure that you are in mute. Unless you have doubts. When you are talking, you can unmute. Yeah. Okay. So now you see that you have a vector 1, 1 and you want to multiply it with some scalar. Let us say you are multiplying with 2. What is 2 times of 1, 1? You have to multiply this 2 to both the components. So what is the resulting vector?
2,
2, 2. Right? Suppose you want to multiply it with -3. Then what is that you are getting?
-3, -3.
-3.
Let us say you are multiplying with 1/2. Then
1/2, 1/2.
Half.
Okay. So in general, whenever you multiply any real number to this vector, you are getting alpha, alpha. Okay. So what happens here? You are, let's say this is this point 2, 2. Okay. And this is -3, 3. Okay. And you have 1/2, 1/2, which is somewhere here. Okay. So what you observe is that all these points, they are lying on one single line. Right?
Yes, ma'am.
Yes.
Okay, they are all lying on this same line. Okay. So can anyone tell what is this line or equation of the line, whatever you call it? What is this?
Y is equal to Y.
Yeah. So y is equal to x is this equation of this line. Okay. So it is not just a special case for this vector. It is true for any vector. Okay. So you take any vector, maybe let us say -1, -2. Okay. So it is this vector here. So now if you are multiplying, let us say by -2, then you will get, what is the answer?
1, 2.
2,
4.
So you see it is along this line. So 2, 4. It's here. So the line is here. Okay. And if you multiply with a positive number, let's say with 1 or maybe 2, also we can do -1, -2, you are going to get -2 and -4. Okay, -2 and -4. Okay, what is the one thing you need to observe here is that when you are multiplying a vector by a positive number, the direction remains the same. And when you are multiplying by a vector by a negative number, the direction is
Reverse.
reversed. Okay, it is still on the same line, but the direction is reversed. Okay, so multiplying by a positive scalar, the direction remains the same, and multiplying by a negative scalar, the direction is reversed. Okay, so maybe I'll write it here. So alpha times, let us say V is a vector and alpha is a scalar. So alpha times of V, direction is same if alpha is positive. Direction is reversed if alpha is negative. Okay. And if alpha is 0, then what happens?
Then it will be origin.
The vector
Yeah.
will become 0.
You will be there at the origin.
Zero
Okay.
vector.
Yeah, you will get the 0 vector. Okay.
Ma'am,
Yeah.
Please
Hello.
give
we
example
only
of
can
one
multiply
reverse
by real
direction.
numbers.
Do we what?
We can only multiply by real numbers. Means scalars can only be real numbers.
For this course, we are considering only real numbers. Okay.
Okay.
Ma'am, why only real number, not complex
Sorry?
number in this data science course? Ma'am, why we use only real number for data
Okay.
science
Why
course,
we use
not
only
complex?
real numbers? Because when you are considering complex numbers, you need to consider what is the field. So many other topics need to be included, for which we don't have enough space within this course. That is why we are restricting only to real numbers. Okay.
Okay, ma'am.
Ma'am, please give one more example
Hello.
for reverse
Ma'am.
direction.
Sorry.
Please give one more example for reverse direction.
See, for example, here you see you consider this vector 1, 1. So in 1, 1, you see that when you are multiplying with the number 2, which is positive, the direction is same. And when you are multiplying by -3, the direction is in the opposite side. For example, if you are multiplying with -1, then you will get -1, -1, which is again in the opposite direction.
Yes.
Okay?
Now understood.
Is it fine?
Thank you. Thank you.
Okay.
Hello, ma'am.
Yeah.
Hello.
Yeah.
Ma'am, how to find component of a vector?
Component of a vector. So this is the first component and second component. What do you mean by finding component of a vector? Simply,
What,
this
ma'am?
is the first component and this is the second component. That's it. Okay.
No, ma'am.
What
I
is
don't
your
know,
question?
ma'am. How to find components of a vector, and how many?
So, what is given to you? I don't. The question is kind of incomplete. What is given to you from which I have to answer this?
I think he wants to ask about angles. Which
Okay.
angle?
Maybe we will come back to it at the end of the session. Okay. Vector in R3. So this is the visualization of R3. So here you have x-axis, y-axis, and z-axis. Okay. So here you see that. So in R2, the visualization is much better than R3. So in R3 here, for example, you see, so this is kind of the point 3 at a height of 2 or something like that. So maybe let us try to draw it here. Okay. So let us say you are having this point 1 comma minus 1 comma 1. Okay. So this is your x, this is your y, and this is your z. Okay. Now for x, the value is 1, and for y, the value is -1. So it is on this side, the negative side. Okay. So 1 comma -1, and at a distance of 1. For z, it is 1. So the point is, this is the vector we are trying to say, 1, -1, 1. So it is somewhere in the space. So it is a 3D space. Okay. So it is a 3D space. Okay. So in R3, visualization is not very simple. It is kind of a floating point in the space. So drawing it in a paper is, you have to imagine it. Okay. So this is how you can visualize things in R3. Okay. Fine. So remember, for this course, that vectors means rows or columns of numbers. So throughout this course, by a vector, usually this is what we are saying, rows or columns of numbers. Okay. Sometimes vectors can also represent matrices, that we will discuss later. Okay. So in general, vectors means rows or columns of numbers. Okay. Fine.
Ma'am, the properties you have told in R2 will also apply in R3. That reverse property, and by multiplying a
Yes,
scalar, it
whatever
will be
properties
in
for
same
scalar
direction.
multiplication and addition, we have seen that applies for R2, R3. So that is what I'm going to write here. So in general, addition in Rn. So if you have two vectors, x1, x2, xn, y1, y2, yn, It is the component wise addition x1 plus y1, x2 plus y2, and xn plus yn. And scalar multiplication in Rn. So let us say you are having a scalar and you are multiplying with x1, x2, xn. So it is alpha times of x1, alpha times of x2, alpha times of xn. Okay, so this is the general rule for addition and scalar multiplication. Okay, so someone may ask, what is then subtraction? Can you tell what is subtraction? How do you define subtraction?
Subtraction of negative number.
So, so let us say you are having two vectors x and y. So x is, let us say, x1, x2, and y is, say, y1, y2. Okay. What is x minus y? So it has two steps. So let us say step 1 is your scalar multiplication
-1
of y by -1. And step 2,
addition.
Yeah,
Add them.
addition of x and minus y. That's all. Okay, so subtraction is nothing new. Subtraction is a concept derived from addition and scalar multiplication together. Okay, or straight away also you can write x1 minus y1, x2 minus y2. It is going to be the same. Okay, it is going to be the same. x1 minus y1, x2 minus y2, xn minus y1. It is going to be the same. Okay, so x1 minus y1 by 2 is equal to x1 minus y1, x2 minus y2. Okay, fine. Okay. Now let us look at this exercise here. At a is equal to 1, 1, 1 and b is equal to 2, minus 1, 4. These are two vectors. Okay. And suppose c times of a plus 3 times of b is given by this. Okay. Here c is some real number, k are also real number. How do you find the value of c? ca plus bb. How do you write this? Right? This is how you are writing. You are just putting what is your a and what is your b here. Now you know how to do scalar multiplication. How to do scalar multiplication?
C, comma C, comma C, plus
6 minus 3
plus 12.
Okay.
And now you have to add these two vectors. These two vectors are from which space?
3.
From these are vectors from R3. Okay. So now you do the component wise addition. So what is the answer?
6 plus c, c minus 3, c plus 12.
Okay. So now you have to compare it with this. So the answer given for this, already they have given the answer as 4, J and K. Okay. So now what is there? C plus 6 is equal to 4. So what is your C then?
Minus 2. Minus 2.
Okay. So you can also find J and K from this. Can you find J and K?
Yes, ma'am. Minus 5 and 10.
K will be minus 2 minus 3, which is minus 5, and K is minus 2 plus 12, which is 10. Okay, fine. Is this clear for everyone?
Yes, ma'am. Yes, ma'am.
Okay. So again, we are having, the same problem. You just have to find the value of J plus K. We have already computed what is J and K. It is minus 5 plus 10, which is 5. Okay, fine. Very simple vector calculations. Okay, so the next I guess the concept of vectors vector addition, scalar multiplication, it is clear for everyone. Yes?
Yes.
Ma'am.
Yes, ma'am.
Ma'am, I have a doubt in pictorial representation of vector, ma'am.
What representation?
Pictorial representation, ma'am.
Yeah, what is your doubt?
Ma'am, like that you are representing R2 in space and R3 in, and when we look at R16, R15, then how can we pictorially represent it, ma'am, on graph paper?
I guess I already mentioned to you that only R, R2 and R3, only up to 3 dimension. That is what you see in real world, right? So the space where you are currently, it is R3. So beyond R3, we cannot visualize. Okay? So only up to R3 we can visualize, and the properties, whatever you are seeing up to R3, you can see everything like in using like arbitrary terms. You can define them. Okay, abstract way, in an abstract way you can see the definition. Sorry.
And if any vector has 4 components, does it mean it has 4 dimensions?
Yeah, the dimension is 4, and all these operations are defined, okay, in abstract way, but you cannot visualize them.
And dimension means what?
What is dimension? That is a topic which is covered in, I guess, some week 4. Okay, not for now.
Okay.
Okay, so with this, let us move to the next topic, which are matrices. Okay, so I guess you are all very familiar with matrices. So a matrix is a rectangular array of numbers arranged in rows and columns. Okay, just like vectors, matrices also play a very important role in dealing with data. Okay, we will see how soon. Okay, so first we will see what are matrices. We will understand the basic properties of matrices, and then we will see how it is used in other places. Okay, fine. Two important notions regarding matrices. An m by n matrix has m rows and n columns. So the first value represents the number of rows, and the second value represents the number of columns. Okay, and what do you mean by ijth entry of a matrix? It is the entry occurring in the ith row and jth column. Okay, if you don't understand with this abstract definition, let us look at the examples. Now, how many rows and columns are there for the matrix A?
2 rows, 3
3 columns.
3 columns, 2 rows.
2 rows,
3 columns.
3 columns.
3 columns. And for B, how many rows and columns?
3
3
rows.
rows.
3 rows.
3 rows.
Columns.
3 rows, 2 columns.
Okay. And for
2
C?
rows, 2 columns.
2 into 2
columns.
Okay. So this is a 2 by 3 matrix. This is a 3 by 2 matrix, and this is a 2 by 2 matrix. And this is what we call as the size of the matrix. This m by n, this is called the size of the matrix. Okay. So what is the size of the matrix means? You have to say this: the rows by the columns. You don't call it into. You call it by 2 by 3 matrix. Okay. Fine. And for example, what is the 2-1th entry in A? Or usually the notation is like this. What is the 2-1 entry in A?
19.
-1. 19.
So you have to look at the second row, first entry, which is 19.
90.
Okay. What is the 2-3 entry? 2-3 entry?
-7.
-27.
-27.
What is your A13?
3.
3. Okay. Now what is your B22?
0.
0.
And what is your B21?
2.
3.
2.
It's 2, right? Second row, first column. 2. And what about B32?
12.
12. And B11?
3.
322? Okay. I guess now you understand what is the ijth entry of a matrix. So the ijth entry of a matrix, let us say A, the matrix A is usually represented as Aij. Okay, and you know what is that? The meaning is clear now, I guess. Okay. Okay. So now, yeah.
I have a doubt in like a definition of matrices. Like,
Sorry.
Ma'am, you said array list of ma'am definition.
He
Sorry,
has
I
a
don't
doubt
hear you.
Definition of
ma'am, he has
matrix.
doubt regarding definition of matrix.
What
He
is the
was
definition of a matrix? A matrix is a rectangular array of numbers arranged in rows and columns. That's all.
Ma'am, here array means only same type of data, no?
See, array means you have like this kind of rows and columns. That is what you generally call as array of numbers. Okay. So you have different kind of arrays means they are kind of like boxes. Okay.
And
So here
array
you
means
have
same type of
Arrangement,
data.
arrangement, no?
So here you see that this you have different rows and columns. This kind of arrangement of numbers. This is what is called as matrix. Okay. All the numbers are represented in rows and columns. Okay.
Array means group, number of groups.
There is what?
Array means groups. Groups of numbers.
Roots of numbers. Yeah, roots of numbers as long as they are real numbers. Yes, we can have them. Whatever real numbers, you can put it in matrices. Okay.
Ma'am, I have a very basic doubt. Can you help me?
Yeah.
Yeah, what is the doubt?
Ma'am, we just had one lecture of array vectors. Then suddenly we moved on to matrices. So what is the role of vectors in data science that we are studying? What is the purpose of studying vectors?
Okay. See, vectors now in a matrix, you have how many row vectors and how many column vectors? So you see that for this matrix A, it has how many row vectors, how many column vectors? 3. 3 column vectors.
Three column vectors and 2 row vectors.
And 2 row vectors. Okay.
Okay, ma'am.
So you see that a matrix itself, they are consisting of many vectors together. Okay. So it is not just completely different things. Okay. And you will see how matrices and vectors combinedly will be used. We will see it soon. Okay. Fine. Okay. So some special type of matrices we will see now. What are square matrices? A square matrix is a matrix in which the number of rows is same as the number of columns. Okay. So here we saw that a rectangular array. It means the size. Please mute yourself if you are not talking. Yeah. So for square matrices, for a square matrix, you see this m by n, your m should be equal to n. In that case, the matrix is called a square matrix. For example, here you have a 3 by 3 matrix. As I told you, any real number can be there in a matrix. So you see decimal numbers are there here. Okay. So the ith diagonal entry of the square matrix is the ith entry. It means what? Your AII. For example, let us call this matrix as A. Then AII is called the ith diagonal entry. So this diagonal term is defined only for square matrices. This diagonal term is defined only for square matrices. Okay. And the diagonal of a square matrix is the set of all diagonal entries. Can you say what are the diagonal entries here? So this is your A11.
0 minus 1. 0.30 and minus 1.
0, minus.
Okay. So these are the diagonal entries. Okay. Now, maybe I will give you an example of a 2 by 2 case. So now here, what are the diagonal entries?
2, 2.
B11 is 2, B22 is also 2. Okay. For example,
Will 3 by 4 and minus 1 also be considered diagonal entries?
Sorry?
Will this 3 by 4 and minus 1 also be considered diagonal entry?
3 by 4 and
-1.
you can call them as off diagonal entries.
Off diagonal. Okay.
Yeah, off diagonal. All the entries which are not diagonal entries, non-diagonal entries are usually called as off diagonal entries. Okay, so this is kind of a terminology only. Okay.
Ma'am, do diagonals also compose a vector?
Sorry?
Diagonals also considered as a vector because they also have a direction.
If you want to specifically do it, you do it, but usually we don't take it. Unless for some specific reason you want to consider that as a vector, you do it, but usually that is not the case. If you want to consider those specific numbers and then you have to define it as a vector, yes, you can do it.
Okay.
Okay.
We cannot visualize this. No?
We cannot
Visualize this like diagonal.
Of course, you are seeing everything here. What do you mean by visualizing? Okay, so like visualizing the vectors, can we visualize matrix in geometrical way? That is what you are asking?
Yeah.
No. See, matrices does not have any geometrical visualization, but it has some other way of visualizing. Okay, visualizing, you can see it as a visualizing in a system of linear equations. We will see it next. Okay, so these matrices are just representing the coefficients in a system of linear equation. That is what we are going to see next. Okay, please wait. So here for this, what is the size of this matrix? Can you tell?
4 by 4.
Okay, 4 by 2 by 2 matrix. This is the 4 by 4 matrix. Now, what are the diagonal entries?
1, 4, 2,
1, 4, 3, 27, 3, 27.
Why cannot 3, 1, 11 are diagonal entries in a different way?
Sorry?
Why cannot, I mean, just off question, why can't 3, 1, 7, 11 be a diagonal? I mean, it is also a diagonal.
No, we don't usually. So this is called the principal diagonal. Whatever we are considering, this is called the principal diagonal. And this principal diagonal is what is considered as diagonal in general. This is considered for some specific research problems, but in general, by a diagonal, we are considering this. And in specific, if you want to say, you can call it sometimes principal diagonal also.
Principal diagonal.
Okay?
Okay.
Fine. Okay, so a square matrix in which all entries except the diagonal are 0 is called a diagonal matrix. Okay, so first of all, for a diagonal matrix, you should consider a square matrix. Let us start with a 2 by 2 example. Okay, so so all the entries except diagonal should be 0. So this is an off diagonal entry, this is an off diagonal entry. So these entries are 0. This can be anything. Okay, so this is an example of a diagonal matrix. A 2 by 2 case. So for
I have a question.
Yeah.
Can a null matrix maybe a diagonal matrix?
Can what?
Matrix.
No.
All the elements are 0.
All the elements 0. Yes, it is also a diagonal matrix. Yes. The only thing you have to see is that the off diagonal entry is 0. Yeah. First of all, it should be a square matrix. Yes. Okay. So,
Ma'am, I have a doubt.
Yeah.
Ma'am, the matrices can be of any size, m cross n.
Yeah.
But the vectors, they can only contain either one row or one column. They cannot be of m cross n size.
As I told you, in general, the vectors in Rn, yes. Vectors in Rn either consist of one row or one column. We are talking about vectors in Rn. Okay.
Okay, so there is no concept of a vector containing m rows or n columns.
See, there is, when you go to vector spaces, you have spaces of matrices. There, each matrix is called as a vector. In that case, what you are saying is true. So that is for a later topic. Of course, you can do that. As I said, when you consider matrix spaces instead of Euclidean spaces, there you can see such concept. Okay.
Okay.
Ma'am,
Yeah.
how null matrix can be diagonal matrix?
How null matrix can be diagonal matrix? What is the only condition you have for diagonal matrix? All the off diagonal entries, all the elements except the diagonal entries should be 0. So here you say except means it can include. Okay, so this is kind of inside bracket, you can say all the off diagonal, maybe the definition diagonal matrix, maybe I can say all the off diagonal entries should be 0. That is the actual. But if you have a 0 matrix, this is also a diagonal matrix only. Okay, this also you can call as a diagonal matrix with the diagonal entry is 0, 0. Okay, but don't worry too much about it. Yes, it is also a diagonal matrix only. Okay, so this is a 4 by 4 diagonal matrix. This is a 2 by 2. Okay, fine. So you can have one of them to be 0. That is also there. All these cases are diagonal matrices. Now, what are scalar matrices? A diagonal matrix in which all the entries in the diagonal are equal is called a scalar matrix. Okay, so it means if you are having
means null matrix. Null matrix is also a diagonal matrix.
Yeah.
Okay.
Okay, so these are all scalar matrices. So scalar matrices are all diagonal matrices. The only thing is that all the diagonal entries should be equal. All the diagonal entries are equal. So for a scalar matrix, all the diagonal entries are equal.
Ma'am, I have a
Means
doubt.
null matrix can also be a scalar matrix.
Yes. A square null matrix. Yes.
Ma'am, we can write scalar matrix as a scalar multiplied by identity matrix, right?
Yes. So any scalar, what is identity matrix? I have to define it and then I can write it in that way. Okay. Fine. So what is an identity matrix? A scalar matrix with all the diagonal entries 1 is called the identity matrix. So for the 2 by 2 case, it is simply this matrix. And for the 3 by 3 case, it is this. And 4 by 4, you know. Okay, so these are all the identity matrix of size 2, 3, and 4. Okay, sometimes the notation is given in this way: I2, I3, I4, or simply I.
Ma'am, can we treat a scalar matrix as a scalar quantity?
No, it is just a name.
Then what?
Okay.
Then what about null matrix? Is it treated as a scalar quantity?
No, it is
Vector, right?
a matrix. Okay, it is just a matrix.
Okay,
Fine. Okay. Okay. Sorry, there was.
Hello.
Yeah, just a minute. I don't know what is going on. I'm just trying to figure out what is going on. Why is this happening?
I think somebody has taken control of your board.
No. is not possible.
Just restart it.
Just give me a minute. I will maybe save it and then open it again. Just give me a minute. I don't know what's wrong.
Anyone will hack your system.
ऐसा थोड़ी ना होता है.
I don't know what was the issue. I just had to erase this unnecessary things here.
No problem.
Okay, fine. So null matrix, it is any matrix. It need not be square. It can be rectangular also. It can be simply even a row vector also. Okay. So even as I did not write this kind of matrices earlier because we were dealing with square matrices. But any row vector or column vector is also a matrix only. Okay, you can call it as row matrix or column matrix. Maybe if I have space somewhere, I can write it. Yeah, maybe here I will write after triangular matrices.
Can I ask an activity question?
Activity question.
Yeah, ma'am.
Maybe at the end, please.
Okay, ma'am. Okay.
Okay. Fine. So triangular matrices. A square matrix with all entries below or above diagonal is called an upper or lower triangular matrix. For example, if you consider a 2 by 2 matrix like this, okay, 1, 1, minus 1, 0. So this is the diagonal. And all the entry above the diagonal is 0. If all the entry above the diagonal is 0, then it is called a... So you have the entries in the lower part. That's why it is called a lower triangular matrix. Okay. Suppose you are having something like this. Now this is called a upper triangular matrix because you see below the diagonal it is 0. Okay. And for the 3 by 3 case, now this is a, can you say what is the type of this matrix?
Lower triangular.
Lower triangular.
Lower triangular.
This is a lower triangular matrix. And this is upper triangular, right?
Yes, ma'am.
Okay.
Yes.
So you know what is meant by a triangular matrix. Actually, there is some kind of notation for this also. Some people also define it using this notations. So if you want, I can write. So for upper triangular matrices, what is this entry? Can you say? This entry, let us call this A. So what is this entry? A?
Non-diagonal.
1, 2.
1, 2. And what is this entry?
2, 1.
2, 1.
2, 1. Okay. So you see that for an upper triangular matrix, your Aij is equal to 0 if your I is greater than j. Does it make sense?
Yeah, ma'am.
Yes, ma'am.
So you see here it is A, A21, it is A31, and this is A32. So whenever your I is greater than J, you see that your AIGs are 0. That is called upper triangular. And for lower triangular, now can you give the condition?
AIG equal to
I
0.
should be
J is greater than I.
I less than. Okay. So you can also define it using these notations. Okay. So next, I will give you the definitions of what is a row matrix and a column matrix. So for row matrix,
AIJ should be 0.
any, yeah.
In upper triangular or lower triangular, AIG should be 0.
So this condition, upper triangular, means Aij is 0 if I is greater than J. So I is greater than J means you see here, this is your I, this 2 is your I, and J is 1. So this 2 greater than 1 means, so this position, all the elements below diagonal. So this represents all the elements below diagonal. And for all the elements above diagonal, you can notice that your I will be less than J. Okay?
Excuse me, ma'am.
Yes, ma'am. Thank you.
Sorry to interrupt. Will you provide the PDF of this session, ma'am?
All the PDFs of every session will be provided to you. Okay? Okay. So any matrix of size, for a row matrix, only one row should be there. So 1 by n is called a row matrix. So for example, 1, 2, -1, no commas for matrix, -1, 3, 5. So these are examples of row matrix. And column matrix, can you give any matrix of size? Can you say what should be the size for column matrix?
N by 1. N by 1.
Yeah, it should have only one column. So example, okay, these are examples of column matrix. Okay. So now looking at where do these matrices occur. Okay. So one of the important application of matrices is to study the system of linear equations. What are system of linear equations? What are linear equations? You have to see everything for that. Okay. So before that, just to see how do they appear, I have given, these are called, this is a system of linear equation. How many equations are there? This is one equation, this is one equation. How many equations are there?
Two equations.
Two equations.
Two equations.
And this x and y, how many variables are there?
Two variables.
Two variables. R2.
Yes. So these are called variables, and these variables are sometimes called as unknowns. Those who are not talking, please mute yourself.
Okay.
Yes.
I have small.
Sorry, what is your doubt?
I have a small request actually. My job shift timings ended at 9 o'clock.
Okay.
So I couldn't join from 8.
Anyway, it will be there in the live streaming. You can watch it anytime you want. Okay.
Oh, okay. Is there any attendance issue or like we are recording attendance?
Yeah, attendance is automatically recorded from the Google Meet, or automatically the attendance will be taken. There is no, and also what time you are joining and what time you are leaving, that will be automatically taken for.
Okay, if there is any shortage, what is the like concession?
The attendance is for recording record purpose only. We'll discuss it at the end of the session.
Sure, sure.
Okay.
Ma'am, where is the live session playlist? I'm not getting it.
I have given the link in the chat box. Please check it.
Okay, ma'am.
Okay. So now you see that this is a set of two linear equations with two variables. Okay. And how do we represent it as a matrix? You write the coefficients here: 1, -1, 5, 2, 4, and 3. Since there is an equal to sign in between, you have to represent it with a line here. Okay, so this is how you represent a system of linear equation as a matrix. Okay, so now can you tell what is the matrix representation for this system here?
Ma'am, what is the dimension for this?
1 minus 2, 5.
5, 10.
So this is a 2 by 3 matrix. 1 minus 2, 5, 10.
10.
Minus
Minus
1,
minus
3,
minus 3, minus 4,
0,
2,
1, 1, 7.
Okay, this is a matrix representation for this system of linear equation. Here you have 3 equations and 3 unknowns. Okay, we will come back to this topic and we have to look at the details of this system of linear equation. Okay. Okay. Now, just like adding 2 vectors, how do you add 2 matrices? The sum of 2 m by n matrices A and B is calculated entry wise. Okay. So, if you have 2 matrices, here there is some mistake. It should be A plus B. Okay. So, the sum of 2 matrices A and B, the ijth entry of A plus B is given by Aij plus Bij. Okay. Always remember, you can add 2 matrices of the same size only. If they are of different size, we cannot add. Okay. So, for example, let us say A is equal to 1 minus 1, 3 and 7. And B is minus 5, 2, 3, 1. What is A plus B?
Minus 4,
minus 4,
8.
minus 1,
6,
Minus 4.
minus 1, no, plus 1.
It is minus 1 or 1? 1, right?
1.
6.
6?
6,
8. And
8.
Okay. Now let us say you have other matrix. Now what is C plus D?
0,
0 minus 2,
0 minus 2,
11,
11, 4, 7,
10.
10.
7 and 10.
Okay. So the size of the matrix is not going to change by addition of matrices. So whatever is the size of A and B, the same is the size of A plus B also. Okay. So the size of the matrix will remain same after addition also. Okay. And for scalar multiplication, it is again very simple. So whatever a scalar you are multiplying, you have to multiply it for each entry of the matrix. So for example, if you are having a matrix like this, now what is minus A?
Minus 1, 3, minus 2,
3,
minus
minus
4.
Minus 4.
And what is 5 times of A?
5 minus 15,
5,
minus
15, 10, 20.
Okay. So this is how you are going to do scalar multiplication. So these concept addition and scalar multiplication are very simple, and this is not going to alter the size of the matrix. But what about multiplication of matrices? It is not very straightforward. Okay. Multiplication of matrices is something very different. Please listen carefully. Let us start with simple matrices. What is the size of this matrix?
1 into 3.
1 into 3.
1 by 3.
And what is the size of this
3
matrix?
into 1.
3 by 1.
3 by 1.
Okay. Now, how to multiply 2 matrices? First rule for matrix multiplication is that suppose you are having an m by n matrix and you are having another p by q matrix. So, A, B, the matrix multiplication is defined only when
M is equal to
M
Q.
is equal to P. Okay, the number of
N
columns
is
of
equal
A
to
and the
P.
number of rows of B should be equal. Okay, so is this condition satisfied for this case?
Yes, ma'am.
Yes, ma'am.
So then we can do matrix multiplication. How is this done? You have to do it in this way. So this row multiply to this column
one.
in the same order. So AD plus BE plus CF. Okay, you can kind of imagine it like a dot product. A, B, C, this is a vector. D, E, F, this is another vector. What is the dot product? How do you define the dot product? AD plus
BE and CF.
BE plus CF. Okay, this is how you are doing. Okay, so the same is what we are going to replicate for the other cases also. Okay, so now can you say AB and CD? What is the multiplication of this? Can you say?
AC plus BD.
ACBD.
plus BD. Plus BD.
AC plus BD. Okay, now if you are having A, B, C, D, okay, and CD or EF. So what is the size of the first matrix now?
2 by
2,
2.
comma 2.
2 by 2. And the size of the second matrix?
2 by 1.
So is the multiplication defined?
Yes.
Yes.
So now you have to do is that first you have to consider only the first row and do the multiplication with this as usual, just like you did here. So what are the entries? Can you tell?
A plus
Please
BF.
Plus
mute
BF.
yourself if you are not talking.
Plus BF
Yeah. AE
plus BF.
plus BF. Okay. And then you have to perform the same for the second row. What is the second row?
CE plus
E
BF.
plus
C
BF.
E plus D.
Okay. Fine. So this is what you're doing. Now, the next case is that what will you do if you are having two matrices, each having several rows and columns? Okay. So let us look at this case, the 3 by 3 case. Okay. So now you have to consider first row with first column for the first entry. Okay, first row into first column for the first entry. Okay, so this is your row 1 and this is your column 1. So this is R1, C1. Okay, row 1, column 1. Okay, so A11, B11 plus A12, B21 plus A13, B31. And now this is your column 2. So this is row 1, column 2. A11, B12 plus A12, B22 plus A13, B32. Okay. And now this is column 3. So this should be R1, C3. Same way, if you have R2, R3, so this is going to be R2, C1. Can you say what is this?
Yes, ma'am. It's clear.
Yes, ma'am.
R2, C2, R2, C3, R3, C1, R3, C2, R3, C3. Okay, this is what you are going to do for matrix multiplication. So, like A be an M by N matrix and B be an N by P matrix, then their product AB will be an M by P matrix. What is the size of the resulting matrix? It will have M number of rows and P number of columns. Okay, so you can notice it in these examples we have done here. So here you have one row and one column. So you have resulting only, this is one single number.
Yes, ma'am. 1 by 1.
Yeah, one number. So this is 1 by 1. And here also you see this is 1 by 1. And what about this one? So the number of rows here is 2 and the column is 1. So it is 2 by 1. Okay. So here it is 3 by 3 into 3 by 3. So this resulting matrix is also a 3 by 3 matrix. Okay. So in general, a matrix M by N into N by P will result in a M by P matrix. Okay. And how do we define the multiplication entry wise? AB of ij is summation I equal to 1 to N Aik Bkj. So for example, what is AB11? According to this definition, summation I is equal to 1 to 3. For this 3 by 3 case, let us say. For N is equal to 3, let us say. A, I is 1, K, B, A1. If you expand, what you will get? A11 B11 plus A12 B21
2.
plus
C13,
A13
A13 and
B31.
B31.
Is this what you are given here? Right?
Yes, ma'am.
Okay. So you can define each entry in this way. Okay. So multiplication of matrices A and B is defined only when the number of columns of A is same as the number of rows of B. Okay. Fine. So let us see some examples here. So what is the size of this matrix? Yeah.
1 by 2.
1 by 2.
1 by 2. Okay. So now let me write. What is the size of this matrix now?
About 2 into 3.
2 by 3.
So is the matrix multiplication defined?
No, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Defined.
It is defined. So what will the size of
Yes, ma'am.
the resulting matrix?
1 by 3.
1 by 3.
Can you say what is the first?
2 minus 6.
Please mute yourself if the surrounding is quite noisy.
Minus 4.
Okay, minus 3 minus 14. What is the answer?
Minus 4.
There is too much noise.
I believe the person inside isn't aware that he is my
Okay. Minus 4, minus 5, and minus 11. This is the answer. Is this fine?
Yes.
So this is what is the size of this matrix now?
1 by 3.
1 by 3.
1 into 3.
Okay. Fine. What is the size of this matrix?
3
into 2.
3 into 2.
3 by 2.
Okay. So now, what is the size of this matrix?
2 by
2
1.
into 1.
2 by 1.
Okay. Now the matrix multiplication is defined.
Yes,
What is the
ma'am.
first entry?
Yes, ma'am.
What is the first entry?
6 minus 1.
3 into 2.
Minus 6 plus 1.
Yeah,
Minus
3 into 6. 6 minus
1.
1. And then
4 minus 3.
4 minus 3.
2 plus 5.
2 plus 5.
5.
So the resulting matrix is 5, 1, and 7. What is the size of this matrix?
3 cross 1 by 1.
1.
3
3 by
by
1.
1.
Okay.
3.
Fine. Okay.
Yes, ma'am.
Just give me a minute. Again, some issues there. Just give me a minute.
Okay, okay.
Suryansh and RH, please mute your mics.
Yeah, someone was asking something. What was that? Okay. So now what is both are 2 by 2 matrix. How do you do the matrix multiplication?
1 into 3
minus 5
plus 0 into 5. Yani 3.
No, see. First row and first column.
3 minus 5
3 minus 5. And then first row and second column. So
minus 2 minus 2
minus 2
minus 2 minus 1.
minus 1. And then here
0 and 10.
0 plus 10. What's wrong? Okay. And then here 0
Plus 2.
over 2 plus 2.
plus 2. This never happened like this. I don't know what's going on here.
Problem in mouse.
I'm sorry, why? I don't know what is exactly going on. Some issue is happening here. This never happened before.
You have to change this mouse.
Okay. So 0 plus 2. So the final answer here is minus 2, minus 3, 10 and 2. So this is a 2 by 2 matrix. Is this fine? Okay. Maybe I'll do some simpler matrix. 1 minus 3, 5. 2, 0, 1. Now what is this matrix multiplication? Yes, what's the answer?
1 into 2.
1 into 3.
0.
The answer is 7.
7.
So I guess the concept of matrix multiplication is clear for everyone, yes?
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
So I have given quite some space. Okay. So I wanted to do this particular problem. So let us consider this as A and B. So this is your matrix A, this is your matrix B. So you have found what is AB. Now let us do what is BA. So 3 minus 2, 5, 1. 1 minus 1, 0, 2. So what is the matrix multiplication? 3 minus 0 and then minus 3 minus 4
Minus 7.
yeah 5 plus 0 and minus 5 plus 2. So you see the answer is 3 minus 7, 5 minus 3. So what about A and BA? Are they same or different?
Different.
Different.
So in general, if AB and BA both are defined, it is AB need not be same as BA, even though the sizes are the same. AB and BA need not be the same. Okay. So this is in general. So matrix multiplication is non-commutative. So this property AB equal to BA, if it is equal, you call it is commutative, and it is not equal, so you call matrix multiplication is non-commutative. Okay, so this is a property for matrix multiplication. Okay, so the next property is that suppose you are having a scalar matrix. Maybe I'll give some specific number here. This is a diagonal matrix. We give a scalar matrix. So let us do the matrix multiplication. Give me the values. Ten. And then here minus 5. And then here 5. And then here 15. What do you observe? What is it you observe?
So scalar multiplication.
The simple multiplication
Yeah.
of 5 into the matrix
Yeah.
second one.
So this matrix is 5. Actually, 5 times of 1, 0, 0, 1, 2 minus 1, 1, 3. Okay. And what is this matrix?
This is identity matrix.
This is the identity matrix. Okay. And you have simply got 5 times of 2 minus 1, 1, 3. Right? This is the resulting matrix. So what is the property of identity matrix you get here? So for any matrix A, okay, so I times of A is equal to I. It's equal to
Screen is lagging. Screen is lagging.
okay.
Ma'am, your skin is lagging.
Fine. Ma'am. Now, what about the other side? Let us consider the same matrix and do the matrix scalar multiplication on the other side. Now, what is the resulting matrix? 10. And then minus 5.
5.
So you see it is again the same. So here
Yes,
you
ma'am.
see that 2 minus 1, 1, 3, 5 times of identity again, which is again 5 times of 2 minus 1, 1, 3. So it means what? A times of I is also equal to A. So what is the property you observe? So this is the property. I times of A equal to A times of I. Okay. So it is not generally for, not necessarily for square matrices. For rectangular matrices also, wherever matrix multiplication is applicable, it still holds. Okay. So this is something you can observe for identity matrices. And for multiplication by scalar matrix, it is simply multiplication by the scalar. Okay. Fine. So these are some properties of matrix multiplication. Now here you see some more properties of addition and multiplication. You have the associative property, you have association of multiplication, and commutativity of addition is there. Only commutativity of multiplication is not there. And whenever you have to multiply by a scalar number, this kind of linearity property is there. Okay. And you have this distributive properties as well. Okay. So these are some properties of matrices. If you want, you can take any 3 matrices A, B, C and verify it. Yes, what is that?
Yeah, ma'am, the second equation that we have in the number of rules, AB in the bracket C is equals to A into bracket of BC.
Which, this last property you are asking?
No, second from the top.
Yeah, this one.
Associativity of multiplication. Yeah. So how is it okay? Like if A, B into C.
So suppose you are having a matrix like this and another matrix like this and another matrix like this. Okay. So now A into B. First you are doing this two multiplication. Okay. And you are getting some matrix. And then AB into C. So let us say X, Y, Z and W is this AB. And AB into C is X, Y, Z, W into this 1, 2, 3, 4. It is going to be same as A into BC. It means what? First you do 1, 2, minus 1, 0. You keep it as it is and do the multiplication of B into C. Let us say B into C is some ABCD. So this, both these values are going to be same. Is it fine?
Yes, ma'am.
Okay. Fine.
Okay, ma'am.
Okay. So next, what is called the transpose of a matrix? The transpose of a matrix is found by interchanging its rows into columns or columns into rows. It means what? If you are having a matrix A, then the transpose denoted by this symbol usually or A dash sometimes, okay, is nothing but A. ijth entry of the transpose is AJI. Okay, so the row and column terms are interchanged. For example, suppose you are having a matrix 1, minus 1, 3. Now, what is the size of this matrix?
3 by 1.
3 into 1.
3 by 1.
Now, what is A transpose?
1 by 3.
Cross 3.
1 comma
1 minus 1 3.
Minus 1 3.
Okay, it is a 1 cross 3 matrix now. The rows and columns are interchanged. So if you have a matrix of size m by n, the transpose will have size n by m. Okay, now let us say you are having a matrix like this. Now what is A transpose?
2, 5, minus 1, 7.
Minus 1 7.
Okay, so here what is A12?
Minus 1.
Minus 1.
Minus 1. A21?
5.
Okay, and what for A transpose, what is the 1 2 element? 5.
5.
Which is 2 1. Right? And for A transpose, the 2 1 element is minus. It is A1. That is what is this definition here. Okay. So one more matrix maybe 1 2 minus 3 5 0 7. Now what is A transpose here?
1 minus 0.
1 minus 3 0. 5 7. 7.
So the size here is 3 by 2 and the size here is 2 by 3. Okay. Transpose what a matrix. Okay. So some simple exercises here. Which of the following statement are true? Any diagonal matrix is a scalar matrix. Is it true?
No.
No.
No. Example?
If the diagonal matrix
is not
So you see, this is a diagonal matrix, but not a scalar matrix.
Scalar matrix.
Right? The diagonal entries are not same. So option 1 is incorrect. What about option 2? Scalar matrices may not be
Incorrect.
square matrices.
Incorrect.
Scalar matrix.
By definition, they
They
should
must be
be
square matrix.
square matrices.
Because
Scalar matrices must be square matrices.
True.
True, right?
Yes, yes. True, ma'am.
Any scalar matrix is an identity matrix.
false.
Identity is when the scalar value is 1.
Yeah, but the converse is true. What is the converse?
Scalar identity matrix.
Identity matrix.
Scalar matrix.
Any identity matrix is a,
Scalar matrix.
yeah. Okay. So you are having 4 matrices P, Q, R, and D. So you have to choose the right options from this given P, Q, R, and D. First of all, what are the sizes of P, Q, R, and D? Let us write down. What is the size of P?
3 comma
3.
3 by 3.
What is the size of Q?
1 cross 3.
1 cross
1
3.
cross 3.
What is the size of
1
R?
cross 3. 3 cross 1.
Again 1 cross 3. What about the size of D?
3 by 1.
Now what is the size of PD?
3 by 1.
3 comma
3 cross 1. So option 1 is
3 by 1. Correct.
so this is
Wrong.
incorrect. The matrix is of the order 3 by 3. Is that correct?
Matrix.
No, ma'am.
Wrong
Incorrect.
matrix 1 by 1.
Wrong.
It is what is the size of QD?
1 by
1
1.
comma 1.
1 plus 1.
Option
So
4.
option 4 is correct.
Yes.
The matrix DQ is of the order 3 by 3. So this is D, this is Q. Is that correct?
Yes.
Correct.
Yeah,
Ma'am.
this is incorrect. QD is not defined. Is it true that QD is not defined? Already we saw QD is of order 1 by 1, so it is
False.
incorrect. What about QR?
Yeah, ma'am. Not defined.
QR is not defined. P plus Q is not defined.
Yeah, not defined.
Okay, thus for addition, it should be of the same order. So P plus Q is not defined. What about P plus D?
It's also not defined.
That is
It's not
also not defined. Okay, fine. Suppose A is this and B is this. Which of the following options are true? P quickly calculate what is A square and B square. Everyone please do it immediately. What is A square and B square? Please calculate and tell me the values.
A square is 1001.
A square is the identity matrix.
Identity. A square.
A square is identity matrix.
1.
Ma'am, A square is 1 minus 1, 0, 0.
0, 0, 1.
0.
0 and 0.
0 and 1.
Yeah.
Okay. 1. 1 0, right?
Oh, 1 0.
1 0, yeah, ma'am.
Identity matrix.
1001. It's identity matrix of second order.
0 and 1. And this is the identity matrix. What about B square?
0, 0, 0, 0.
0, 0, 0, 0.
Okay, so it is the null matrix. So
Yes,
option 1 is correct and option 4 is correct. 2 and 3 are incorrect. Suppose A is a 3 by 3 scalar matrix and the 1 month entry of the matrix A is 4. So what is the matrix A? Can we precisely write from this given information?
Only diagonals are 4, 4, others are 0.
So the diagonal, all the diagonal entries are 4 because it is a scalar matrix. If the first entry is 4, the other diagonal entry will also be 4, right?
Yes, ma'am.
Okay. So this is your matrix A. Now suppose B is a 3 by 3 square matrix such that ijth entry is equal to I squared plus j squared. So B is a 3 by 3 matrix. So can you tell what are the entries of B?
2,
0.
0. How it is 0? It is I squared plus j
I
squared.
0 is 0.
Yes, ma'am. 1, 1,
5, 10.
1, 1,
Plus
2.
1 square.
2.
1 square plus 2
Plus
square.
2 square, 1 square plus
Square
3
plus
square.
and here 2
2
square
square plus
plus
1
1 square.
2 square plus 2 square, 2 square plus 3 square. 3 square plus 1 square. 3 square plus 2 square. 3 square plus 3 square.
So 2,
5,
5,
10,
10.
3, 5,
5,
5,
4, 4, 8,
8,
4, 9, 13.
30. 10, 13, 12. No, 10, 13, 18.
10,
10,
13,
13.
4, 9, 18.
Okay. So this is the matrix B. Now what is 2 times of A plus B?
2 times
10.
0, 0, 8,
10,
0, 0.
8.
This is your 2A.
Okay.
10, 5, 10, 5, 16, 13,
5,
10,
16,
13, 24,
10, 13.
26.
16,
26. 10, 13, 26. 26.
26, 26.
Okay. So now the question is what is the 2 entry of 2A plus B? So 2A plus B 2 is
16.
16.
okay.
16.
Fine. So is there anything special about the matrix B?
Yes, ma'am. Ma'am,
What is
the
the
upper triangle and lower triangle are same.
Yeah. So what is that you observe? You observe that Aij is equal to Aji.
AJ.
Transpose 1.
I is not equals to J.
Not.
So Aij is equal to Aji. So you see that. So this type of matrices, which means what is the A trans? Sorry, not A. It is B. So here you see that Bij is equal to Bji. So what is B transpose in this case?
B.
B.
Same thing.
Okay, there is a name for this kind of matrices. They are called symmetric matrices. It is a very important class of matrices. So what are symmetric matrices?
The matrix transpose equal to matrix.
The transpose is equal to matrix
Square
itself.
A square
matrix.
matrix transpose.
A is symmetric if A transpose is equal to A.
A.
Yes, ma'am.
Okay.
Ma'am, is skew-symmetric?
Yes. All right. So what are skew-symmetric matrices then?
A transpose is equal to minus A.
Minus of A.
Yeah. A transpose is equal to minus A. So for example, if you take this matrix 0, 1, minus 1, 0. This is your A. What is your A transpose?
0 minus 1.
1 0.
1 0.
So your A transpose is minus A, right?
Okay, got it, ma'am.
Okay, fine. Let us do the next problem. Suppose A is minus 1, 2, minus 4, 7. Okay, and A squared minus alpha A plus I is 0. For some alpha in R, find the value of alpha. So quickly compute what is A squared. And then you have to do A squared minus alpha A plus I. What is the answer?
6.
It's 6. 1 minus 8. It's not 6. 1 minus 8 minus 7, right? The first entry. We are saying the final answer.
Yes,
It's minus 7, 12, minus 24.
Minus 7. Here
12.
minus 2. Yeah, 12.
Then
4,
24.
minus
Minus
24.
24.
41.
Minus 8. Okay, this is your A square. So minus 7. Minus alpha is here. Now your minus 1. So plus alpha. And then you have 12. And then you also have this. Plus 1. So 12 minus 2 times of alpha. And then minus 24 minus or plus 4 alpha. And then here 41 minus 7 alpha plus 1. Okay. And this is given as 0. So what is the value of alpha then? So if you use this term, 12 minus 2 alpha equal to 0, which will give you alpha is equal to 6. Is this fine?
Yes, ma'am. Yes,
Okay. So here just a note here. What is trace of a matrix?
Trace.
Sum of principal diagonal.
Sum of diagonal entries, I think.
Sum
Yes, ma'am.
of
Sum of the diagonal matrix.
diagonal entries. So if your trace is defined only for square matrices. Suppose you are having an n by n matrix. Okay. Trace of A is equal to A11 plus A22 plus ANN.
ANN.
Okay. So in this case, what is the trace of this matrix?
Principal diagonal.
What is the application of this?
6.
Okay.
6.
What is the trace of this matrix?
M.
Okay. So maybe with just this one problem, I will wind up the session. We will just give an introduction to
Ma'am,
how. Yeah.
Can we ask activity question now?
Let me just complete this part, and then if you still want to continue, we can do it after winding up the session. Okay. So
Excuse
I'll
me,
just give
please
you.
down a page
Ma'am,
for
can
a
we get the
second.
slides after the session?
Sorry.
Ma'am, can we get the slides after the session?
Yes, yes, you will get it. You will get it.
Okay, thank you.
Okay.
Please down the page for a
Can you
second.
please tell about the attendance format or attendance thing, because my shift is ends at 9 o'clock, so I
Please
couldn't
don't
join.
worry about the attendance. Don't worry about the
Slides of this session.
Okay. So shall we continue? Please hold on. I will just complete this. Okay.
Ma'am, please down the
ma'am.
page for a
Yes,
second.
ma'am. Please continue.
Okay. So here, what is a system of linear equation? So system of linear equation means it generally arises in many real world scenarios. Here is a very simple example here. Okay. The cost of a ticket to the circus is rupees 25 for children and rupees 50 for adults. Okay. So on a certain day, attendance at the circus is 2000 and the total gate revenue is rupees 70,000. So the question is, how many children and how many adults bought tickets? Okay, this is the question. So let us say, let X denote the number of children
1200 and 800.
and Y denote the number of adults. Now, what is the information given to you on a specific day? The total number of people are given to be 2000. So with this notation, what can you write for this statement that the total number is 2000?
X
Yeah,
plus
have
Y equal to
plus
2000.
Y is equal to 2000. Okay, and the total gate revenue is rupees 70,000. So how do you calculate the revenue? So for example,
25x plus 50y
yeah,
equal to 20,000.
25x plus 50y is 70,000. Okay, so now what you have obtained is a system of linear equation where you have two equations and how many unknowns are there? Two unknowns. Okay, this is a very simple scenario where you see that system of linear equations are occurring. So many scenarios, this kind of system of linear equations are occurring. Okay, so first of all, what are linear equations? A linear equation is any equation of this form. Okay, so where you have the coefficients are a1, a2, an with the variables x1, x2, xn. Okay, so these x1, x2 are the variables or unknowns, and these are the coefficients b, a1, a2, an. These are the coefficients. So this is the linear equation. And what is a system of linear equation? If there are multiple linear equations combined together with the same set of variables, then it is called a system of linear equation. Okay, for the same set of variables, if you have different coefficients, then that is called a system of linear equations. Okay, so in this case, 2x plus 3y plus 5z plus 9, this is a linear equation where these are the variables, and what are the coefficients here? 2, 3, 5 and 9. And here, what are the variables for this equation?
X and Z.
X and Z are the variables, and what are the coefficients?
1, 3, minus 7. 1 minus 3 minus 7.
These are the coefficients. Okay. System of linear equations means you have several equations. For example, here you have m linear equations with n unknowns. Okay. So this is a system of linear equation. Already we have said that this system can be written in this way. Okay. So with this I stop with a small homework here. So here you see that you have a matrix A, you have a column vector X, and you have a column vector B. So do the matrix multiplication AX and verify whether you are getting AX is equal to B. Okay, when you do the matrix multiplication, these are the elements you should get. Okay, do this matrix multiplication and verify whether you are getting AX is equal to B if you are using these vectors. Okay, do this as a homework, and now we will end this session. Before ending this session, please make sure that before the next session, complete the week 1 videos. Okay, and whatever doubts you have, you can ask me now, or you can ask the TA or the next instructor also.
Ma'am, have you have an
And
idea
when will the next lecture?
when the next
Sorry?
session will help?
The next session is on Sunday.
Okay, ma'am.
Timing? Timing 8:30 to 9:30. Sorry, 8:30 to
Activity
10:30.
activity